Recording in progress. Okay. Okay. So last week we did mini prep, right? So did everybody completed the mini prep? Yes. Okay. Now everybody okay, good. Um the DNA preparation that you've done is the smallest scale. That's what we call mini prep or something like that. But if you need more DNA, then there are higher level kit that you can purchase. There's one up, called MIDI prep. There's one called Maxi prep. There's another one called Giga prep, and no, Mega prep, and then the largest one is Giga prep, I think. So the difference between different kit is just the amount of DNA you can get at the end of the purification. So for example, like your mini prep, probably you expect to get somewhere between like five microgram of DNA, something like that, which is good, more than enough for what we're trying to do in the class. But if you want to do, I don't know, like if you want to make an RNA vaccine, for example, or DNA vaccine or gene therapy type of thing, that 5 microgram is not enough, right? You need more, right? So this is why some people go to the higher, higher yield type of kit. For example, like the Amgen Biotech experience when they supply plasmid to high school classroom, they don't do mini prep. They usually do at least maxi prep. So they do maxi prep. That way they get the scale that the yield that they usually get is around like milligram ish, or at least like 0.5 milligram or something like that. So that's what the yield for the maxi prep. So anyway, but now that you've done mini prep, at least what's important is every single step, which we discussed last week. Be sure to know why we add certain reagent, because that become very important, right? The principle is very similar between one kit and the next. So if you know if you're used to one kit, it's very easy to translate that to different kit. So it's very translatable, I guess, right? So it's good. So at least you guys learn about the mini preps. Now the question is, after you've done all those procedure, how much DNA you get, right? So, and today we are going to talk about exactly that. So basically we have to QC your mini prep. So how do we do that? So let me share my screen number 4. There you go. Okay. So you see my thing. So you have, this is my, okay. So you have your DNA. How much volume do you have? Do you guys remember? What's the volume you get? Where's the What is the last step that I think you put the elution buffer, right? Remember that the very last step after you wash with the plasmid wash buffer, you remove all the ethanol, right? And then after that, you add small amount of the elution buffer, the EP or something like that. And I remember in the lecture video, I said that you have to aim it at the very center, that white circle, you have to aim it over there. Do you guys remember the volume? I don't really remember. No, nobody remember the volume. Nobody. Okay. I think it's about 30 microliter or something, 30 or 50, something like that. So let's just say it's 30 microliter. Okay. Let's say I don't know what the actual volume that you use. But let's pretend it's 30 microliter, right? So now the first thing we need to do is we need to measure the concentration of your DNA in the tubes. Now, how do we do that? Well, luckily, you guys already learned about absorption spectrum. Remember, last time you worked with dyes, and we use certain, like an unknown dye. Each group has unknown dye, and then you explore the absorption spectrum curve, right? And then you determine the lambda max. Remember that? But the lambda max, anybody remember what is lambda max? What is lambda max? Anybody remember? What is a lambda max? The maximum absorption number is not quite, but okay, it's maximum absorption number. It's not exactly lambda max. Anybody else remember? Where's my soundboard? I think I have my soundboard. There you go. Okay. What is the anybody? Yeah. All right. So lambda max, if you remember, that is the wavelength, which is what lambda is. Lambda is the wavelength at which your solution or your liquid absorb the light the most at that wavelength. But again, lambda max is the wavelength at which your solution absorb light at maximally, right? So for example, like if you remember, you have a dye, an unknown dye, and then you get something like this peak like that, right? And then you get this peak right there, and then you go down here. This is your lambda, right? Wavelength. So, and then this is your absorption spectrum or something like that, right? Absorption, and then this one here, when you go down right there, that's your lambda max for the solution. Again, it's the value in the x-axis right there, the lambda max. Oh, by the way, you need to know that one for your final. Remember that, right? So again, that's the lambda max is the wavelength at which your solution absorb maximum, at the maximum absorption, I guess. So how do we quantify your DNA? Well, luckily for you, DNA also have their own absorption spectrum. For DNA, the lambda max for DNA is, anybody know what is the lambda max of DNA? Anybody know? This number you really need to know, okay, by the way. Lambda max for DNA and lambda max for protein. Because this is very, very common in the lab. If you work in biotech lab, molecular biology lab, biochemistry lab, most of the time you will work with protein or DNA. And one way to quantify this is using the absorption spectrum like this, right? So this is why you need to know this number specifically. So let me tell you this time, but you have to make sure you write down, okay? The lambda max for DNA is 260 nanometer. Whereas protein lambda max is 280 nanometer. So both are in the UV range. This is why UV, people tell you UV can cause cancer, right? What happens is that UV, when they strike your body, your DNA absorb it, okay? And then when it get absorbed, there may be some chemical changes that will trigger a mutation, and that mutation eventually accumulate to give you cancer, right? So this is why we wear the sunscreen. But anyway, so again, the DNA absorbed maximally at 260 nanometer, whereas protein at 280 nanometer. Okay, so what we do is we're gonna use essentially kind of like spectrophotometer, kind of like that, right? To measure your DNA concentration, and you learn from the previous activity, you can have some sort of correlation between concentration and the absorption, right? And that relation is what is being spelled out in what we call Beer's law, right? Beer's-Lambert law. Remember that? Right? The absorption equal to the extinction coefficient. Right? This is the epsilon. Extinction coefficient times BC. Some people call this ABC formula, right? So A equal to epsilon BC. The A is your absorption. Remember this. And then the B is your path length. Path length. So like if you use your QFAT for the spectrophotometer, the path length has been measured 1 centimeter. Remember that? That's what I told you. You have to put the QFAT in one way, the arrow faces the light, something like that, right? Because if you switch it the other way, the path length will be smaller, and therefore you get the wrong number. And the concentration is the C. This is your concentration. And this is why for each solution and at any given measurement, since you use the same machine, the same QFAT, most of the time your epsilon and the B are constant, right? This is your constant. And by doing so, your absorption is proportional to your concentration. The higher your concentration, the higher absorption you get until you reach that, what is that called, the maximum, the upper limit of the linear range of your spectrophotometer. This is why you have to dilute your dyes when you work with them, right? The first time you receive your unknown dye, you have to dilute them first before taking the first measurement. Otherwise, you will be outside of the linear range. I hope you still remember all that, okay? So because this is why, I don't know if you know that, we started you off in the second half with the absorption spectrum, because that's the foundation of everything, okay? Almost, not everything, almost for a lot of things, okay? Including DNA measurement, protein. Even when you work later on with the fancy machine like HPLC or FPLC, you know, a lot of those measurements are UV-based measurement, right? So when your protein come out, they absorb it at absorption 280, right? For the protein here, 280 nanometer, right? So and this is why you have to know this concept really, really well. That's the foundation of a lot of things in the lab. Okay. So all right. So how are we going to measure your DNA concentration using this Beer's law? Well, as you know, you probably remember when you did your mini prep, the amount of DNA you get is very small, right? It's probably in a tube like that, microfiche tube. It's about 30 microliter, right? But then you remember when you put your dye, when you work with the dye last time, the QFAT, you have to put one mil, right? Do you have 1 mil of DNA? No, right? Your DNA amount is only 30 microliter. So you don't even have enough volume to measure your DNA concentration using QFAT. So what do you do? Well, luckily for us, we have a cool machine, you know, that we call NanoDrop. So today we are going to use NanoDrop. Okay, I'm going to show you how to use NanoDrop. It's quite fancy equipment. There are other way to do it. Like there are other way to quantify DNA. The one that's also quite popular is using this machine called Qubit. We will have Qubit. We just don't have it now yet, but at some point we will have Qubit. But today I'm going to show you how to use NanoDrop. Ideally, NanoDrop is available in the lab. Usually you don't move them around generally, right? But we only have one. So I have no choice but transport it to Reseda, back to us, and then next time to Venice and back to us. Yeah, it should not be transported often like that, but it is what it is. Okay, so why is it called NanoDrop? Because it only require you to put a small amount, only 1 drop, if you will, of liquid to measure the concentration. So the device look like this. Maybe I can show you here. I brought this one home right here. So this is the NanoDrop. Some of you probably have seen this if you see the what is that called? Maybe I should, you know what? Maybe I should stop sharing so you can see me bigger. There you go. Okay, you can pin this. Okay, so that's the NanoDrop. Okay. And the first thing that you can see right here in this screen, there are different modes. So this is if you want to measure double-stranded DNA right there. I don't know if you can see, it's kind of glaring. So that's for double-stranded DNA, that's for single-stranded DNA, that's for RNA, and then that's if you do microarray, we don't have to worry about that right now. This is if you want to custom make the protocol, some oligo DNA, oligo RNA. So if you measure primer or something like that, use this one. For us, we are going to use double-stranded DNA. And by the way, they're all in this nucleic acid. So here's the nucleic acid, right? There's other one. If you want to use this for protein, you can use this one. Just click over there. It goes to protein. There's protein at 280 nanometers. See this one, absorbance to 80, right? Because protein absorb maximally at 280 nanometer. You can do other stuff like Bradford reagent, PCA, Lowry, and things like that. So there's this special mode for that. Some protein label if you want. So that's for the protein side. And then you also have OT600. This is for bacterial growth. So if you want to measure bacterial growth, it's in the OT600 right here, right there. And you can custom make this one too, right? UV vis like this one, the one that you do the absorption spectrum right there, just like with your spectrophotometer, right? You can use this one here with the UV vis right there, right? And then, of course, there's another one for kinetic. If you want to measure some chemical activity, you can do all that, okay? But today, we're going to do nucleic acid right here, okay? So how do you use this, okay? Well, the first thing is you want to go to the double-stranded DNA mode because we are using plasmid, and plasmid is double-stranded DNA. Yeah, maybe I should. Okay, this is so you don't have like my email in the background. Okay, let me close this one. Okay, there you go. All right. So, okay. So, yeah, you want to click the double-stranded DNA, this one right here. Just click, boop. Okay, and then it will tell you have to clean both pedestal and load blank. Okay. Now it says auto blank is on. So this one here, auto blank, auto blank here. And then the blue one here is on right there, right? Let's see. If I can make it stand. Oh, slow down. There you go. Okay. Okay. So, all right. So the first thing that you need to do is you need to clean the pedestal right there. Right? So what is the clean the pedestal mean right here? Clean both pedestal, right? Well, here over here. Okay. So if you open this, the first thing you notice is you have this. Oh, hello. That's a minion right there. So actually, this one can also be used for a QFAT. So this you can put the QFAT right here. So that's for the QFAT if you want. Today we don't use QFAT because our sample is very small. So this is what they meant by pedestal right here. So this is the place where you load your sample right there. Okay, and this is the first pedestal, and the second pedestal is the one on the here. I don't know if you can see right there. Yeah, right there. See, that's one, and then there's another one. So both pedestal must be clean because the light will travel from there to there. So I don't know if you notice right here. There's that little hole right there. You can see. There you go. Right, there's a little hole right there. That's the optic right there. Okay. The optic basically shoot the light just like a spectrophotometer. Okay. The light gets shot from one, and then from here, and then go to the other one, and then they measure the what is it called, the absorption. Okay, so how do you clean it up? Well, first you want to squirt with this water, just distilled water, right? Just squirt that one. You don't need much, just a little bit, something like that, you know. And then now you need to wipe it with Kim wipe. So I brought Kim wipe here. By the way, you have to wear gloves, okay, when you actually do this in the lab, because be touching all this other stuff, not in the comfort of your home, right? You're in the lab. So here you use skim wipe, and you have to clean the bottom, right? There's a lot of water, and you want to clean the top first, also the top as well. Here, so just clean it like that, okay, and then you need to dry them using the dry part of the skim wipe. I notice I use the same Kim wipe because I can. Yeah, just use the dry part of the Kim wipe to dry them up, right? And then what does this say? Says? Okay, so once you're done, this one can go to waste bin, something like this. I'm gonna have something like this to put at your waste bin. Now it says, what does it say? Lower the arm to measure blank. Okay, so you have to lower the arm to measure your blank. So the arm is right here, right? This one right here. So you have to measure your blank. So what blank do we use? Well, ideally the blank should be your the illusion buffer. So that's what you should use for your blank. But if you want to use water, it's okay too for this, because it's not that much different, I guess. It's always good to use the same liquid that your DNA is in, but if you use water, it's not going to be the end of the world. Okay, you want to put about 2 microliters, so I'm adjusting my micropipette here. Let me see. Yeah, between 1 to 2 microliter. Ideally, you should put 2 microliter, but even if you put 1.5, it will work just fine. Okay. All right. So now I'm gonna take my blank. Let's pretend I take blank somewhere. Okay. Think about my blank right here. Okay. Second. Okay. I'm just gonna put the blank. You have to aim it. Okay. When you put your blank here, it has to be right on top of that. Okay. Ready? Here you go. Okay, and then throw it in here. Okay, so now did you see that one? The liquid just right there sitting right there. So the drop has to be that one, really beautiful on top of the pedestal, right? Has to be like that. You have to see something like that. And yet this is the part where you have to be very observant. You have to observe everything very carefully, right? So now once you have the blank over there, you lower the arm. Now notice, once I lower the arm, this one goes up, right? Yeah, there you go. And then it measure it. It's blanking, says blanking, blanking, blanking. Okay. And then after that, you need to clean both pedestal, and auto measure is on right here. Auto measure. It means once you close it, it measure it automatically. You don't have to press measure all the time. If you don't like it, you can actually turn it off. Yes, that now it's off, right? So if it's off, then every time you close it, you have to press measure over there. So that's the difference, okay? If this is on, the moment you close it, it measure right away. But if it's off, you have to press the measure. Okay, why don't we just do it, okay? So let's say, I blank it already, and I want to see what happened to the concentration if it's blank. It should be 0, right? In principle, it should be 0 if you have your blank there and you just measuring your blank. Okay, let's see if it's really 0. So let me just open it, okay, and then I'm gonna close it again. This is still the same liquid right there, right? And close it again. So essentially, your nanodrop just measured the blank, right? See, so this is automatic measurement on, right? So I just close it measure right away. Okay. Well, you see the number right here? Can you see it? No, you cannot see it. Oh, never mind. Maybe if I shine the light, maybe it helps. No, it just glare more. Oh, epic fail. Okay. Okay. Let's see. No. Cannot see it. Okay. Well, if you can see it, it's 0.3 nanogram per microliter. And there are the other 2 number over here. So this is the unit. That's the concentration. I know you cannot see it. This is not good. How can I make it less blur? Less. There you go. Yeah. See, the one is nanogram per microliter. You see over there, it says 0.3, which is 0.3 nanogram per microliter, which is close enough to 0. That's fine. And then next to it, it says absorbent 260 over 280, and then absorbent 260 over 230. Okay. So there's 2 number that I want you to pay attention, because we're gonna discuss that next. Okay. Okay. So let me share again. What is that? Number 4. Right. So the blank, when you read the blank, there are three things, right? The DNA concentration at nanogram per microliter, and this one, it says what, 0.3, which is, close enough to 0. That's good. And then that is the absorbance to 60 over absorbance to 80. And then there's, I should put this one, another column that's absorbance to 60 over absorbance to 30. Okay, what are all these? Okay, well, if you remember, absorbance to 80 is where protein absorbed. So here, right? This absorption to 80 is where protein absorbed, whereas absorption to 60 is where your DNA absorbed, right? So and this is why the absorption to 60 and to 80 ratio, this is very, very important, because this tells you how pure or tell you the purity of your DNA. Okay, because remember when you do your mini prep, you pop the cell open, and then now you have a mixture of DNA and protein, right? So and you have to purify them so you get as much DNA but not protein, right? So if you get too much protein, then your absorption to 80 right here become high, and therefore the number become low and quite low, right? So whereas if you get pure DNA and you get very small amount of protein, then your this ratio would be high, essentially. How high is considered pure enough for DNA mini prep? Generally, 8 to 60 to 80, you want it to be about between 1.6 to 1.8 approximately. So if you get your absorber to 60 to 8 to 80, about 1.6, 1.7, 1.8, generally you can be very confident that you have pure DNA. Will you get that? Well, that's what we don't know, right? You can imagine if you don't, let's say if you skip the plasmid wash buffer, right? And then you get a bunch of protein, well, guess what? Then your 8 to 60 over 8 to 80 would be much lower, because you have high value, that large number of your A to 80, the denominator. Your denominator will be bigger, therefore you get less than 1.6, right, of that ratio, right? So that if you get your ratio 8 to 60 to 80 ratio less than 1.4, for example, then your prep is pretty dirty. You got a bunch of protein there, most likely. Okay. Now, sometimes you can get more than that. Like you can get like a ratio of 2.2 or something. Generally, RNA absorb more at 260 mole per mole of the molecule. They absorb more. Generally, if you get up, the 8 to 60 to 8 to 80 ratio higher than 2, like 2.2, 2.4, generally you may be getting quite a bit of RNA contamination, which may or may not be a big deal, right? Depending on what experiment you want to do. But that may indicate that maybe someone did not add the RNAs in your buffer or whatever, right? So that's that's one of the way to tell whether you get a good purification. Okay. Now, again, going back to this, as you see, the 8 to 60 to 80, let me just move this one for the blank. For the blank, you get what, 0.3 for this, and then 0.85 of 8 to 60 to 8 to 80, close to 1, which is telling you that it does not absorb at all in this wavelength, right? And then this is like the 260 to 230 is for this one is 0.09. That one just tell you about the background, right? The background absorption at there should be nothing virtually absorbed at 230, right? Except a few small things, right? But then generally you should expect to get absorption at that wavelength. So if you see some absorption, then there may be something wrong. Right? So anyway, so we expect this to be close to 0, which is, for blank 0.09, which is good. Okay, so now you need to measure your DNA. So how do you do that? Well, here is where I'm going to show you again. Boop. Okay, this is so difficult right here. Okay, so this one still have my blank. I don't, if you see that one, the auto measure, I still put it on, right? I can turn it off if I want. Okay, I turn it off now. Okay, so now we need to clean this one. How do you clean it? So again, use the Kim wipe. Use your Kim wipe. Open this. You have to wipe the bottom and the top. Remember, this one right now it only has blank, quote unquote blank, right? But if this one has your DNA, then you have to clean it even more, because then you don't want your DNA to contaminate it, to messed up with the reading for some other group, right? So when you in the process of reading everybody's DNA concentration, you need to clean it well. Okay, so again, the first thing is just wipe it like this, and then squirt it with water enough, something like this. Okay, and then I usually absorb it, and then just wipe it like this, and then go to the top as well, something like this, and then use the other dry part of the Kim wipe to dry it. This. Okay, and then once you're done, just throw it over there, and then you're ready to put your sample. Okay, so let's try one more time with the sample. So, well, I don't have a sample right here, so it's just gonna be the same water that I have. So again, take cube like that, and then put it there. Put over here. That. Okay, so if you look at that again, that one's nice, right? The drop is really nice, and then just close it. But because remember, I put the measurement auto measure off over here, so when I do that, boop. Oh, by the way, did you see this? Okay, let me see here. See, when you close this, the bottom and the top pedestal, your liquid should form a column. Did you see that one? Right, you see it right there, right? So the bottom pedestal and the top pedestal, and then your liquid just touch that, and that create a column of liquid, and that's the path length. The path length, I think, is about 1 millimeter or something like that for this, which is different than your spectrophotometer. The path length is about 1 centimeter, right? This one's about 1 millimeter, right? Which is right there. See, yeah, there you go, right there, right? So now the moment once I press this one right here, the measure, when I press that, what happened is the bottom one, the bottom pedestal is gonna go up, and then it's sort of like squeeze the drop, and then it start doing the measurement. Okay, let me press it, and then you can see the movement. Okay, here you go. Are you ready? Here we go. I press that one. Oh, yeah, see. There you go. It press it so that now it's exactly 1 millimeter, right? And then it gives you the reading. Now the reading is kind of bad for this because it's just water, right? So it's only minus 0.5. And then 860 to 80 is 1, which means there's no difference between the absorption at 260 versus 280. There's no difference. And yeah, so anyway, and then the background, and yeah, so, and this one also gives you the graph, right? This big graph right there, right? So you can, this is one view. You can switch it to the next one. Oh, what's that? There you go. That's another one. That if you want to display it in the sample number 1, 2. If you have multiple sample among different group, you just swipe you swipe left, essentially. You go swipe left, and then you go here, swipe right, you get that. Okay, just swipe left. Okay, so that's basically it. Very simple. And then yes, very simple. And then you want to get the reading. Okay. So now let's go back to this. What happened after you get a reading? Where's my pointer? Yeah. Let's get number one. Okay. What happened after you get the reading? What is considered good reading, right? Well, for a mini prep, generally it depends on a lot of things. The good DNA concentration for a mini prep can be generally between 150 to about 400 nanogram per microliter. Okay, and it depends on the plasmid, right? If you have so-called high copy plasmid, you can get up to 900 nanogram per microliter, maybe even 1,000 something, right? So that's possible, right? Yeah, so now here you can actually calculate your DNA yield. So the one that again, I don't know what's the volume of my DNA, of your DNA, your elution buffer. I just remember it may be that your elution buffer is about 30 microliter. I don't know the exact number, right? But if you let's pretend the volume is 30 microliter and your DNA concentration, let's say, this is how to calculate DNA yield, right? So let's say the volume that you get is 30 microliter. Let's just pretend, since I don't remember what's the volume of your elution buffer. And then the DNA concentration from the nanodrop, DNA concentration, let's just say, I don't know, 250 nanogram per microliter. How are you going to calculate the concentration? The yield? Well, it's very simple. So, your DNA concentration, your yield is essentially 250 nanogram per microliter, and you have 30 microliter, right? If you really have 30, I don't know what the volume is. You have to check your protocol to make sure you get the right number, right? So if you do that, then it's gonna be like what, 77500, something like that. What, nanogram, which is about 7.5 microgram. Okay. And that's basically how you do it, how you calculate your yield. So any question? The max, okay. Okay. Yeah. So if you get at least, about 5 microgram, it means you're doing good job. Okay. Generally, it's for mini prep between 5 to 15. I think each column is different. I think for certain company, they say the maximum yield you can get is 20 microgram. Some says 25, some says 15. So if you can get 10 above, that's good enough. 7.5 microgram, that's also good. And you need to put this number in your lab notebook. Okay, this is one of your documentation. And then in addition to this and the concentration, right, you have to write the concentration from the nanodrop. In addition to these two number, you also need to write down your A to 60 over A to 80 ratio. Okay, so you need that number in your lab notebook. Okay. Now, is that enough? Well, not really. Well, I think it should be enough if you do it with the mini prep kit. But for us, we will try to do one more step to really visualize your DNA and to make sure that your number is not coming from a bunch of RNA, right? Right. So how do we do this? What else do we need to do? Well, we are going to do gel electrophoresis to see it. So for this, I will also bring the kit like this. You're gonna have that one, right? You just need to make one gel, I think, for everyone. How many groups? How many groups do you guys have in the class? eight groups. Okay, and then each group you do 2, right? Each group doing what? Pecan? No, 7. Yeah, remember you have what? Each group only do 1, right? One purification, one plasmid. One of them is a pecan R, and the other one is piara, right? Is that correct? Is my calculation or my recollection correct? Okay, good. So basically, you should get some. Technically you just need 8 wells, right? So if you notice this, you need to make your gel later on, and when you cast your gel, you have a choice. Maybe I should turn off this one. Oh, here, okay. So, right. So when you put your comb, you have 2 choices. You can use this one. You get bigger comb right there, right? But you get less well, right? Whereas the other one, you get a smaller comb, smaller well, but you get more, right? This one is about 27 or so, and this is about 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, yeah. 14, and the other one is 26 or 28, I don't remember. So for you, because you only have 7 sample or 8 sample, this one is good enough, right? You can even skip every other lane, right? Maybe this is group 1, group 2, group 3, group 4, 5, 6, 7, and you need 1 well for your ladder. Okay, DNA ladder. Okay, what is by the way, this is your DNA ladder. I already make it for you right there. I've taken aliquot from the lab right here. It's called 1 kb DNA ladder. So what is this? Oh, and I also have a writing over here. You need to yeah, load 5 microliter per well. Okay, so for you just need 5 microliter to run one of this, right? Now you may ask me, what, Dr. K, what is DNA ladder, right? Well, DNA ladder contain multiple fragment of DNA with known molecular weight, with known size, essentially. And the purpose of that is it will allow us to compare your DNA fragment to your ladder, which is we know the size of. So the specific one that you're gonna use is called 1 kb DNA ladder from NEB. I can show you here. I can give you the link right here. Let me see if I can put the link. So you may want to take a look at this. I'm gonna put it in the chat. What's that? Okay, in the chat right there. I'm gonna share this. Share screen number 3. Okay, right here. Okay, so this is your DNA ladder. As I mentioned, they have the multiple fragment at multiple size. You will need that information in your notebook, by the way, right? This one has 10 different DNA fragment with different size, starting with 0.5 over here. There's 0.5, and then you have 1 kilo base pair. That's the unit kilo base. So you have can I no? Right, there's 0.5 over here. There's 1 over here, 1.5 kilo base, 2, 3, 4, 5, 6, 8, and 10. Okay. So if your DNA runs somewhere in the 3000, right here, for example, then you know the size of that particular DNA fragment you see on the gel is about 3000, okay, or 3 kilo base pair. Okay, I already give you the link over there. Make sure you save it. You will need that information for your when you run your DNA. Okay. All right. So what was another thing I want to tell you? Well, again, you need to make your own gel, right? Just like when you try to do dye electrophoresis. But remember, for the dye electrophoresis, you put the comb in the middle, right? In the middle of the gel. Here, you want to put it at one end. Don't put it in the middle. Okay, you put it in one end. That way, you get enough space to separate your DNA fragment. Okay, and not only that, remember, unlike dye you can see the color, right? DNA is colorless. You can't see the color, and this is why you need to add a dye. You need to add DNA dye, okay? And the DNA dye has to be kept in the dark, okay? And the DNA dye we use is here called gel green, like the gel green DNA stain. We put them in the dark here. So once you're done, you need to put it back over here, okay? So here, and you can see, they give you very little. Who is that? Ooh. Yeah, this one. See the red one right there. They give you very little, and yeah, I think this is what is this? Oh, this is 10,000x. Yeah, yeah. Not this. I think there's a thing here. As you can you see this one, the writing? 10,000x, 10,000x GG. GG is not good game. Okay, this is gel green. All right, 10,000x gel green. Okay, and that's the lot number. This one is the lot number right there. Okay, so yeah, so you have to do the proper dilution because this is 10,000x, and the agarose gel that you're gonna make for that one tray is 40 milliliter. So you can calculate. You know what? Maybe I should write it down. Okay, let me here just the number for again my notepad. So remember, for just to review, you're gonna make your gel, right? You need to calculate the amount of agarose gel, right? Put agarose basic, and then wait, you're gonna mix it with 1x SB, right? Remember, don't mix it with water, okay? If you mix it with water, it's not gonna run. All right. This time you have to mix it with water. With 1x SB, and then you want to make about 0.8% agarose at the end. So you have to calculate how much agarose you need to put over there to make 40 mil. 40 mil. So that's the volume. 40 mil is generally enough for one tray. Okay. And then from there you have to calculate how after you microwave it, right? You microwave it, to melt the agarose. And when you melt the agarose, just like when you did last time for your dye electrophoresis, this is the same thing. You melt it, make sure it's you know, all your DNA. Oh, sorry, all of the agarose has been completely melted, right? You can swirl it, you know, and then make sure there's no speckle floating around. Oh, that I also forget. Oh man, I did not bring the heat gloves. Let's hope Reseda has heat glove, okay? You don't want to touch this one because this is hot, just like last time. Remember that? And then once you once you melt it completely, you want to cool it down, cool a bit, cool it a little. Basically, you want to make sure it's cool enough to the touch, but it's not too cold to the point that it's solidified, right? Because that's bad, right? And then after it's cool, you add the 1xGG. Add, well, you're gonna add that 10,000x. You have to add some amount to make 1x. I'm gonna let you do the calculation. I don't want to just tell you how much volume you need. You have to calculate how much 10,000x gel green you need to add to create that 1x gel green in your 40 mil agarose, okay? And then once you do that, you pour, okay? And then after that, you let it solidify, okay? And then you can run the gel. Okay. Now, what is your expectation? Well, is there any questions so far? I know I sort of like going one after another. Any questions so far? No question? Okay. All right. So what do you expect to see, right? Well, for this, well, what you expect to see is this, right? Oh, shoot, I forgot to bring the The imager. Oh man. But I think I saw you have the imager at Reseda, I think. I remember I see the imager. I may be wrong. Let me see if I can find the imager there. Okay, anyway, let's go back. Basically what you need to do is once you run your gel, you need to transfer your gel to the imager, because remember, unlike dye, for dye you can just see it. You can see it there, right? DNA is colorless, you can't see it, right? So this is why we put the dye, the gel green, but even then you're not going to be able to see it without a special device, and that special device is what we call UV trans illuminator. So basically what you do is very simple. The device is just something like this, right? And then this is your UV light right here. This is your UV light. UV light, or UV or blue or UV light. Okay. And basically you want to transport your gel over here, put it over here. And usually there's a shield. This is your shield, because you don't want to blast UV to your eye, right? Because then it's gonna be creating mutation. This is why I think a lot of kids, a lot of trans illuminator now no longer use UV. They just use blue light, which is, you know, not as dangerous as the UV light. But nevertheless, you have to put the shield still, even though it's blue light. I still want you to put the shield, and then you turn there's the button, on off button, something like that. You turn it on, and then the UV or the blue light coming from the bottom, blasting it to the top like this. And then if if you have DNA, your DNA will bind to your gel green dye, and because it binds to your gel green, it's gonna fluoresce, right? And therefore you should be able to see on the gel where your DNA is. So it will look like something like this. Let's say this is your DNA gel, okay? Just this is the well. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are more, right? I'm just trying 9 over here. So usually people load well number 1 as your ladder. Oh, by the way, I want you all in your notebook to have what I call loading scheme, okay? Or gel loading scheme. Meaning like who load in where, who loads their sample and where, in what well it is, right? So that once you have the loading scheme, you know, once you get your result, you can just compare it to your loading scheme and you see, okay, that's my sample right here, that I see the band right there, so that's mine, right? If you don't have the loading scheme, it's gonna be disaster. Like, where's my dye? Where's my DNA, right? So anyway, so usually for most people, they usually run the ladder in the first well. Let's just something like this, right? So let's say this is what 0.5, then what 1, 1.5, 2, 3, 4, 5, 6, 8, 10, right? So you see something like that, just like, remember I showed you this one, right? So yeah, 10, 8, 6, 5, 4, 3, 2, 1.5, 1, and 0.5, right? You should see something like this. That's your ladder, right? You should see this in your ladder, right? Now, you will have your let's say group 1. This is group 1, and this is what, I don't know, pecan R. And then maybe group 2, also pecan R. Group, I don't know, I just make up group number 6, maybe you do P-ARA, and then group 7, also P-ARA, right? So what do you expect to see in here? Well, in order to answer that question, you need to know the size of your plasmid, which I don't remember the size of the plasmid, but you can easily look it up, right? In here, let's just take a look at this, okay? Where is the Biotech? I can see from here. Where's Reseda? Right. Okay. So if you look at in the module on Canvas, you have your Amgen Biotech experience. Where's that? Protocol, the one that I showed you last time. Where is that? Yeah, Amgen Biotech right here in the digest. Loading. So slow. Canvas is so slow. Anyway, doesn't want to work with me. Yeah. Okay. All right. So this one, right? You can see from here, P can R is about 5,500. PRR is about 4,872. Okay. So knowing this, just move this one out here. Because your can R is about 5,500, it should be a little bit above between this 5 and 6 right here. Should be between there, maybe about here. So you should see a band, ideally something like that. Okay. Whereas the PRA is 4,872, which is slightly below the 5,000, which is slightly below here. It's gonna be somewhere like this. Okay. Now, ideally, you expect to see only one band because your DNA is pure, supposedly. But you may have multiple bands, as you can see later on. I don't know what you expect to see. Sometimes you see bands that running lower than your expected band, for example, something like this, okay? And that one indicate what we call supercoiled DNA. Right? Sometimes in the cell, your DNA just be packaged very tightly. And because it's packaged very tightly, they run much faster because they're more compact, right? They run much faster in your gel, and therefore you see the second band, seemingly lower molecular weight. Also, occasionally you see some DNA that's a bit in the higher molecular weight. That can happen if your DNA is what we call multimer, right? So for example, like this E. coli, when they divide, they grow, they copy their DNA from 1 to become 2, but the 2 is not quite separated yet. So they kind of like making a multimer, and that's why you have higher molecular weight. So that can also happen, although the amount may be less. So what I'm trying to say is, even though ideally, like if you want to do in the test, in the exam, you just draw one band at whatever the size that is, in reality, you may see multiple bands. Okay, and that's the reason why is because DNA can be a different conformation, either supercoil or multimer. Okay, and that's gonna be the fun part. So I think I'm going to stop here right now. If you have any question, you can ask them right now, or I'll see you guys tomorrow.